Cool. All right. Hi, everyone. My name is Adrian. I work here on Cloud Foundry, but I'm not going to talk about Cloud Foundry. I don't want to bore everybody. Um, Before I get started, too, I want to thank Zach and Matt for organizing such a great meetup. And if this is your first time here, welcome. So today I'm going to talk about Go and robots. So, you know, why would you use Go for hardware, right? You always hear about writing CLIs, web services, that kind of stuff. But Go is actually a really great language for hardware for the same exact reasons why you would use it for a CLI or a web service. It's strongly typed. It has very strong concurrency primitives. The deployment story is, second to none. And the most important thing is cross-compilation is incredibly easy. So using Go, you can target different OSs and platforms with using the Goose and Gorch command line args, which if you're at GopherCon, that's the official pronunciation of the build command line flags, according to Rob Pike, the guru himself. So, a lot of people ask, how do you actually program devices using Go? So a lot of people have done, you might have done some hardware programming in school, or just heard about it. And, it has something to do with bits on, microcontrollers and something like that, right? So Go cannot be used for bare metal programming, right? So that's something like you would use for C, C++, Rust is another new up-and-comer for that kind of stuff. So you're going to need an operating system. Now that can be embedded Linux, that could be Windows IoT Core, that could be basically anything that Go supports running on some device somewhere, right? So there is a project that hasn't been updated in a long time, but it's a version of Go that runs on the Artem's RTOS, which an RTOS is a real-time operating system. So that allows you to have some amount of OS niceties on top of a bare CPU. So then you can have some very, basic support for networking, things like that, which there's problems with running Go on that right now, but in the future that might actually work, and that would be really exciting because you can use a whole other class of hardware devices. So for this talk, we're going to be talking about non-bare metal programming. So how do you actually communicate with hardware using Go? So there's a few different ways that you can do this. I listed a few up here. Basically what this amounts to is, if you're on Linux, Linux supports, or it provides you some OS primitives that you can use to access files, device files that communicate to some hardware device. So if you remember from Unix class, everything in Unix is a file. So pins are a file, network devices are a file, everything's a file. So programming a hardware device in Linux is just reading and writing from a file like you would do anything else. There's other ways that you can communicate with hardware devices. One's a remote serial interface, which is if you've ever programmed an Arduino using a language like JavaScript or something like that, or Ruby. That's a remote serial interface. So you're actually sending bits down a serial interface and receiving bits from a serial interface to do sort of a client-server type thing. And a lot of new hardware devices have built-in networking stacks on them, and they might be communicating to some back-end system, like Particle. They used to be called Spark. That's a really great hardware platform. You can do most of your communication through HTTP. So you can actually do a combination of writing some C code, or they're starting to support Rust, directly on the device, and then exposing that via an HTTP request that you can write some Go code to execute that remotely. So those are sort of the common ways of doing that. So the current landscape for device programming and Go is sort of scattered, right? So it's still new. There's a lot of people doing cool stuff in there, but it's sort of all over the place. So there's a lot of one-off libraries of people writing support for different hardware platforms or specific, devices. There's a few different frameworks out there that, you might have seen some talks about them, and they support a lot of great devices, and the getting started experience is phenomenal. And those are great for getting started. But the problem is that as you get into the internals of these libraries, some of them aren't very idiomatic Go. You can't easily port from framework or library to another framework or library. And if you want to add hardware support to those, it's a nightmare. So here's a link to a repo that has a whole list. It's sort of like an awesome Go type thing, but specifically for hardware. And it's just filled with different types of frameworks, platforms, devices, everything like that. So it's a good resource for seeing what is available out there. So what I'm going to talk about in this talk is the new Peripheral IO Go packages that are in the exp IO package in the Golang org that a few people are working on. So the purpose of this project is to set up a base level of interfaces and implementations for common hardware platforms, specifically doing I2C, SPI, GPIO, things like that. So it's not necessarily flying drones and doing all this crazy stuff. It's using sensors on common hardware platforms to build IoT products or physical device products, whatever you want to call it. IoT is the cool new thing. So here's a few links for some of the repos that I'm using here. So the exp IO package, that's where core implementations exist for communicating with GPIO and I2C SPI devices, and a few reference implementations for communicating to Linux, for instance. Yeah, okay. So yeah, I'll talk about a few of these. So I2C. So this is a serial interface for communicating with hardware devices. So I think it stands for inter-chip communication. So that's what most common hardware devices used in your phone, for instance, use. It's maybe some board with a little microcontroller on it that has some sensor on it, and you actually send and receive bytes to it to get temperature information or light information, things like that. SPI is another sort of similar kind of thing, except it uses one wire. I2C uses 2 wires. GPIO is just the general digital reading and writing of things like LEDs, buttons, etc. PWM, that's how you regulate how much voltage is actually sent to a hardware device. So if you think about a dimmer switch when you turn a light on or off, right? So a lot of times what that does is it's sending maybe less voltage, or it'll be at a different rate than you might normally have, or regulating speed, things like that. So it'll actually pulse it with some energy for a while instead of having constant on. So these are sort of the bread and butter of all hardware device projects and anything you can buy. So a few of these things up here, sysfs, devfs, formata, this is all just Greek to everybody. And so basically what this is sysfs. When I mentioned earlier that on Linux operating systems, it exposes a bunch of files which correspond to physical devices that are plugged into your platform. That's, you might have some pin or some file on your Linux operating system that corresponds to a pin on your board. devfs is something similar, but it's using Linux syscalls to manipulate things. And Formata is a remote serial interface for communicating with an Arduino. So I'm actually going to use these 3 ways of communicating to do some hardware demos here. So yeah, these 3 repos, all of it's open source. It's still a work in progress, and everyone's very much invited to help break everything, contribute, tell us that we're wrong, and make something good out of it. Okay, so let's do a couple demos here. So the first thing I'm going to do is program this Raspberry Pi. So if you haven't seen a Raspberry Pi before, this is a Raspberry Pi. So it's an embedded Linux computer. They were originally designed for cheap computers for education purposes, but hackers love them because they're 25 bucks, and you have a Linux computer that you can create, any type of physical device application that you want. It supports most of the common sort of I/O types of things that you'd want to do, except for analog, but that's all right. So this thing on here, this is called a PyGlow. So this is just a really fancy LED with an I2C controller on it. So normally you might have LEDs that are blinking on or off, but what's better than having an LED? An LED with a microcontroller that's driving it. So I'm programming a computer that's programming a microcontroller that's driving a light. So that's pretty cool. All right. And this giant thing is just my battery pack. And I've got it plugged into my laptop here through Ethernet because, I don't use Wi-Fi. OK, so I've got a couple example programs here that I'm going to show. Let's see here. I've got so many tabs. Actually, I'll just show it on this. So here's a gist that I can share this link for everybody to see. But here's a program that I wrote that is sort of the hello world of physical device programming for organizations that TDD like Pivotal, right? So I did not TDD this application, so I'm a fraud. But this application is going to show us the current build state of a repo that I created using this Raspberry Pi. So then if this thing is shouting at you that you just broke the build when you push a commit. So let's start going through this application. So first I have my main, which each Go program has an entry point of a main, that this is what gets executed first. And what I'm going to use here is a few different packages, right? So let's see here. I'm going to use this I2C devfs, right? So this I2C devfs, if we look here, comes from the exp IO I2C. So when I talked about I2C earlier in devfs, so this is actually using devfs functionality in a Linux operating system to allow me to control an I2C device. And I'm passing that into this pyglow.open function, which pyglow.open is a package, or Pyglow is a package that's in the Go IoT devices repo that is where sort of all of our devices that use the exp IO, like low-level communications. So you can implement things like Pyglows. So the general format of how this works is the exp IO package will have raw base implementations of how you communicate to a Linux operating system, for instance. And then packages would be built on top of that that will implement specific protocols for devices like the Pyglow or motors, things like that. So the good thing about architecting it this way, which we'll see a little bit later on, is that this open function accepts anything that conforms to the I2C interface, which I2C interface has a couple methods like write, read, etc. So right now I'm passing in a devfs implementation, but if I had a different type of device, let's say a Windows device, Windows IoT Core, or an Arduino, or something similar to that, I can actually pass that in, use the same exact code that's driving this application, but now it's running on a different hardware platform. So we're going to see an example of that a little later, but this is designed from the ground up to support multiple hardware platforms with minimal code changes necessary. So this main routine should be, it's not very magical. It's I open up my Pyglow connection, I set up my Pyglow. So different devices have different ways that they're set up. Some of them might need to restore registers. Some of them might need to do some initialization process. And you might not want to couple that with your open routine. So this one, we have to call an explicit setup. And then I just have a basic for loop here, which is going to clear out all my lights. I'm going to call this check function, passing my Pyglow into that, and I'm going to sleep for 3 seconds. So let's look at what check does. So check is actually the function that communicates with Travis and checks out what my repo is doing. So check is accepting this notifier, which is a color notifier interface. So this interface is expecting methods or functions that have these functions on them: yellow, orange, red, green, and blue. So there's no magic in how you pass around these hardware devices in a Go program. It's just like anything that you've done before, right? So it's interfaces, structs. It's just all the same. It's all Go code. There's no magic associated with this. So anything that implements these interfaces can execute this function. So if I had a PyGlow, or if I have some other type of RGB LED, or if I had some type of, SVG drawer on my screen, I can just pass it into this function, and it'll actually do what it's supposed to do. So I created a repo here called shipit. And so shipit breaks all the time, but it doesn't matter. So we could look at here. So I got my shipit repo here. And if you're curious about shipit, it's the best adder function in the world. So, but, somebody broke it. I'm not going to blame this file. And I got a basic test in here, which is basically just, 2 and 2 should equal 4, and if not, ship it. And I got my Travis up here, so it's a broken build. So this is going to hit Travis's API. It's going to make the request. It's going to do JSON decoding, just like a normal Go program. And then Travis is going to give me back the last build state. So that's going to be the state at which my, the last state of my repo, which is pass, failed, started, or created. And default is just the catch-all for if something weird happened. And I'm just going to set these colors depending on what that state was. So I'm going to run this program. So earlier I mentioned the ease of cross-compiling a Go program. And I previously compiled this program. I'm going to increase this. I previously compiled this program and just SCP'd it onto my Raspberry Pi. So I didn't install any of these libraries. I don't have Go on here, nothing. I just put this binary on here, which, I could actually do it in front of everyone. Just takes a little time. But you pass in arguments like Goose is Linux, Gorch is ARM, and for Raspberry Pi you have to do Go ARM is 6, and you do your normal Go build. So same tool chain, everything. You just say, okay, cool, I want to target this, different hardware platform. So let's run this notifier program. So it takes a second to load up there. Okay, cool. So if you can see here, my build is red. Oh, wow. That's it's broken all right. Wow, this is crazy. Wow, let me try this. I know, this is like, oh, here we go. Cool. All right, so it's red, which we all knew, because 2 minus 2 does not equal 4, hopefully. So I'm just gonna kind of do one of these jobbies. Okay, cool. So every 3 seconds, it's gonna check the repo and it's gonna reset the light depending on what you're doing, right? So since I'm, somewhat of a developer, I figure out, all right, I got a minus sign in my add function. So I'm gonna actually increase this size here. I'm gonna open up shipit, and I'm just gonna replace this with a plus, and then I'm gonna not even run my tests because it works, right? I'm gonna commit, gotta add shipit. I'm gonna push. So there we go, GitHub. So then cool. So then this application's running, and we can see here, that it's still red. So Travis hasn't queued up this application yet. So when it turns blue, that means that, okay, so Travis is building my application right now. So this is going to take a few seconds. Let's see here if I can put Travis up in the, oh, dang it. If I have Travis here, we can see here Travis is building my application, and I have my light that's blinking. Let's see here, it's still running. So, Travis, I'm on a free plan. Takes like 1,000 years to run anything. And hopefully this didn't break. Wow. Oh, nice. Look at this. Right when it passed, it's like, nah. Let's rerun this. This is actually why you should check your errors and not just panic out if something goes bad. But, you know. Oh, cool, it's green now. So it sort of worked. Yeah. So this could be yours too for like, I don't know, $50 or whatever this costs. Cool, okay. So that's kind of an interesting little project, right? So you can see how that's sort of useful somewhat, right? Build notifier, everyone wants that. Everyone wants to know when they've messed up at work and just in front of everyone's face, right? So, you know, let's move on to something that's a little bit less, I don't know, blame-inducing. So this is going to be a, everyone here loves Twitter, right? Or whatever. So we're going to use a Twitter program that's going to be driven by an Arduino and an LCD screen. So let me do a little zoom in. I'm glad you asked that question. So an Arduino is I'm going to open this thing up. So an Arduino here, this is an Arduino if you've never seen one before. So an Arduino is a microcontroller. It has no operating system on it. It has very little RAM, CPU power, everything like that, storage. It can only run C programs. But if you remember when I mentioned earlier that one of the programming schemes that you can use when programming devices in Go is a remote serial interface. So some clever people created this program called Fermata. So Fermata is a serial protocol that's loosely based off of MIDI format, which is used for controlling, you know, like sound devices and stuff on your computer. And they created a remote serial interface program that allows you to control the pins on an Arduino. So you load a C program onto the Arduino, and then you run a Go program from somewhere else. So the Go code does not actually run on this board. The Go code is remotely controlling this board. As opposed to this Raspberry Pi, the Go code was actually running on the board itself. So this is autonomous, right? This is a client. So somewhere you have a server that's controlling this device. So that could be, in the case of my example here, that's going to be a local serial cable. That could be Bluetooth. That could be Wi-Fi. That could be some other type of communication scheme. So I'm going to send commands to this Arduino to tell it to do stuff, right? And so what I got here to connect things, this is called a Grove shield, and this is an LCD screen. So what's nice about using Grove, I'll just take this thing out here. So Grove uses these little connectors called a Grove connector. And what it does is it's just this tiny little ribbon cable that makes it easy for you to plug devices together. So if you've ever done anything like this before, you might know breadboards or soldering or things like that. So it's a pain, especially when you're trying to just develop something. Grove connectors are really easy because to plug things in here, you just kind of Lego it in there like that, and then you're done. It's connected. And then the same thing here. This is an I2C device. So you can see it says I2C on there. I'm just going to plug it into I2C the right way. It's like a USB cable. You got to flip it over 3 times. And then this just plugs into the pins. You know, it's just like a pass-through. I'm going to plug this thing in here like this. Cool. And then the Arduino's got a couple plugs back here. One's a barrel jack for power, and one's just a USB cable. So I'm going to plug this into my computer here. Let me see here. Plug this in. Cool. So let's go through this program a little bit before I start running it. So, you know, I go on Twitter occasionally, and sometimes I don't always like to look at my phone. So it would be cool is if I had a little screen here that would just very inconveniently show me tweets at any time that I wanted to see them. So I wrote a program to do that, because that's what I like to do. And I wanted to do it in Go. So I spoke at this talk, or this thing. So let's see here. So I'm going to use this Anaconda library, which is the first library that I found for communicating with Twitter's API. I don't know why it's called Anaconda, but it works well enough, so, you know, I don't know, use it, I guess. So we're going to have the same type thing that we do here, right? So I didn't want to leak any credentials to my real Twitter account, so I'm using os-get-env here, which this just reads environment variables off your system. And I'm going to do the same sort of pattern that I did with the Raspberry Pi, which was I have this Fermata.new device, which is like the I2C devfs that was on the last example. And I'm going to pass that in to a device opener. And so this open is another device in the Go IoT package. And instead of using the exp IO package for my devices, my device implementation, I'm going to use this other repo that I created called HAL, which stands for Hardware Abstraction Layer. And I created a Fermata interface, or Fermata implementation that implements all the same I2C interfaces that the official exp.io packages implement. So using this, I can actually pass in a different implementation for a different hardware device into these device drivers so they can work with Linux or Fermata. And as far as the program's concerned, nothing has changed. It's just this one line of code is the only difference that you need to change the target of the hardware device that you're programming. And so this is the address of the Arduino, which it communicates over serial. And this is the baud speed of the Arduino, that's the speed in which it can do serial communication. So baud speed's not really important. So first thing I'm going to do is open this up. Then I'm going to set my RGB LED to all white so we can see it easily. Then I'm just going to have a giant for loop that's going to get a tweet. I picked this hashtag because it had a lot of activity. So this is for the Democratic Convention that's going on right now, but we can choose a different hashtag. So this was top trending at the time I wrote this. So we're going to search for anything that has a hashtag of that. We're going to clear the screen, set it back to home, so we're just going to start from a clean position. And then every time we get a tweet, we're going to print this out to the console so I know the program's actually working. And that's another thing that you should do in each of your programs. You should have some type of logging at the start of your program so you know that it's actually working. Because I don't know about you, but every time I run a program that has no logging, I have no idea if it's actually doing anything. So you should probably write some type of logging, just like, hey, I'm running right now. And then what I'm going to do is pick off characters or runes off of this tweet.txt, which is the actual text. And I'm going to do a little math-magic here, where the top line of the LCD screen only has 15 slots for characters. And when I reach the end of that, I just want to restart to the front of the screen. So I'm going to clear the screen out. And then what I'm going to do is I'm going to set the position to position 16, which is the bottom row of the LCD screen. And I'm going to put the person's name who did the tweet. And then I'm going to set position back to 0, so it starts writing on the top line. And then I'm going to write the character. So what this means is the top line of my LCD screen is going to stream the tweet, and the bottom line is going to have a static text of the person's name who tweeted out the message. So it's just going to be this kind of cool little animation that's incredibly hard to read. And then I'm going to put a 100 millisecond delay in between each character so you can sort of read it. And then I'm going to sleep for every 2 seconds afterwards, or else Twitter will just reject my token. So let's run this program. So I'm going to go back here. Yeah. So I'm going to actually close this one out. We don't need that. And then I'm going to clear this, bump this up a little bit here. So I want to make sure that I'm actually communicating to the right port. So tty dot, oh, don't want that. Yeah, it's like, you're using Mac, we know better. I want to make sure 1421. Yeah, cool. Okay, great. Wow. Okay, go run main. And so this time, I'm actually just going to run the program on this computer, right? So let me see here. There's actually a little bit of a bug with this program that the first time you run it, I run it and then quit it immediately and then run it again and it works. So, you know, it's a little, don't look behind the curtain. Let's see here. I don't know why this isn't working. Let me just restart this thing. Yeah. Whenever none of this stuff works, you just plug it back in again. Okay, cool. So it turned on. I'm going to run it again. You already knew I was going to do that. Okay. Oop. So now I'm going to actually do this. So you can see here, I've got my screen. Oh, no. So this is kind of, let's see if I can do this. All right, cool. So let's see here. We've got some Twitter screen on here. It's by Bella. Serenade. Yep, women's rights. That's cool. And so she's talking about Hillary. All right, this is like one thing at a time. So this is kind of cool, right? But if you notice that we get the same tweet twice in a row. Oh, wait, here's a new one. Huffington Post. It's all about Clinton. So this is a pretty cool little Twitter program. But the problem is that every 10 seconds, I'm just getting the top tweet, right? So I can miss Twitter messages. So I only get a new Twitter message every 10 seconds or more. So if I want to have more messages, or if I don't want to miss anything, then I got to have some type of queue, right? That I want to actually read through all of these things. So I wrote another program to help with that. So let's look at that. So I'm going to do something a little more complicated here. I'm going to close this program. And this program is almost exactly the same, except I wrote this little thing. I heard about Go routines in Go, and I heard that you can use them for concurrency, so I thought I'd try it out. And I don't care about sharing state between two different threads, so I'm just sharing a map. So, you know, what could go wrong? So I'm going to do the same kind of thing before, except this time I'm going to take 10 tweets, and I'm going to assign them into a map. And every Twitter message has an N64 ID that is, you know, a unique ID. So I'm going to just store the key as a unique ID, and then I'm going to store the tweet. So I'm just going to have this key pair. And then I'm going to do the same exact thing that I did before, except now, instead of calling Twitter messages in this for loop, I'm just going to pick off of the tweets that I already found. And this one is going to sleep for 1 second instead, or else it just goes too fast. And I'm just going to constantly loop in one for loop, reading messages. And then in another Go routine, I'm going to be populating the structure with more tweets. So hopefully I don't miss any tweets. So let's see what that looks like. So I call this program Q. Let's see if this works. Oh, no. You gotta, oh. It's because I gotta do, that's the thing with Arduinos, is if you plug it into a different USB port, it changes its address. So, you know, always plug it into the same USB port no matter what. So I'm gonna run my Q program. Okay, cool. So, nice. Oh no. Let's see, can he zoom? Okay. Cool, so then we got a Twitter message here. And then, nice, so I got a different one this time. Yes. Yeah. We can do a different hashtag if you want. Yeah, so this person is very into Metallica and Hillary Clinton. So, So that's a little Twitter bot, right? So those are just a couple example programs that I wrote just to show how easy it is to use some existing libraries to control hardware devices for, these were toy examples, but everything I did in these examples maps directly to a real hardware platform that you might work on, right? So it's network communication, writing to I2C devices, displaying information, having some type of input and output. That's basically what every single hardware application out there is. It's you get some information and then you blink a light depending on what it is. And that's pretty much every single IoT and phone out there, right? So that's it. Thanks.
So do you or anybody you know have done any kind of like benchmarking in terms of cycles, for example? The runtime. Did anybody benchmark it at all?
Yeah, so I've like a double. There we go.
What?
Okay. Yeah, so the question was basically energy usage and its impact on these devices. So I know that from previous experience from myself and other people working on these, a lot of times allocations and stuff like that wasn't at the forefront of our minds because we were just trying to get something to work at all, right? And then after that, then you iterate from there, which is different than the exp packages that we're working on. Is now we're very aware of allocations and all that kind of stuff, right? So there's varying levels of that, right? So obviously, if you're running a Linux with Go runtime and all that stuff on there, it's going to use more power than if you're running just a C application on an Arduino. So your battery usage or your energy usage is going to be higher, especially too if you have multiple threads going on at the same time. So if you're hyper battery aware, then you probably have very specific requirements that you want to go for that. But we are keeping that in mind with these packages because that's a very real problem for a lot of hardware devices. I just blew all of your minds. They have nothing to say. Yeah, so if you go to the Gopher Slack, which I don't know if all of you are members of Gopher Slack, so there is a Go IoT channel that myself, Mattson, a few other people, so we're there to talk, and we do have a repo Go IoT devices that you can submit issues, talk to us through that way. So that's probably the best right now. I don't know, Go Nuts or something, or yeah. Yeah. So for the exp package, so there's actually right now it just implements Linux, right? So any Linux device, it should work, and Brillo is basically Android, which internally at Google they're working on that, but that's not out yet, which hopefully we can get some open source Android working. And then I just pushed Fermata on there. So right now it's limited to Linux and Fermata. But I've been talking to the Windows IoT Core people to try to get some more information on programming Windows with Go. which I guess no one's tried to do that before. So I got like jockeyed around in this email chain for like 2 weeks. Cool. Any other questions?
Yeah, I was just wondering, essentially all the libraries we discussed are more or less wrappers around serial connection for the most part.
Not always. So in the case of the Arduino, so it's using a serial protocol. So yes, it's communicating through the serial, but the device or the library implements that protocol to send bytes down the serial interface. And for instance, for the Raspberry Pi, this is using devfs syscalls in Linux to do that. So at the end of the day, it's either a serial port or a file or something that you got to communicate through, or the OS. And then we've written the implementations using those raw primitives to communicate with the devices.